Today, we're really excited to hear from McCrum, who is now at the Chemical and Biomolecular Engineering Department at Clarkson University. So he did his PhD at Penn State and his postdoc at Leiden. I think we all know that through his collaboration with Mark Coper. And he specializes in surface science and electrocatalysis for energy conversion, wastewater treatment, and production of chemicals. And he uniquely does both experiments and computations towards a fundamental understanding of electrochemistry with the aim of designing better devices. And so with that, I'll give the floor to Ian. So thank you again for giving us this talk.
Perfect, thank you. And thank you for the introduction. And thanks to Karen and Nitish for inviting me to come and present here today. Just give me a second to get set up here. So thank you. Thanks for the introduction. It's nice to also see some familiar faces in the audience. So thanks to everyone for joining. So I would like to present some of the work that I've been doing over the last few years, looking at predominantly the effects of cations and electrolyte pH on activity and selectivity in electrocatalysis. I'll also talk about how solvents plays a very important role in mediating those effects. I'll say hopefully everyone can hear me. So I'm, as Karen said, I'm now an assistant professor at Clarkson University in Potsdam, New York. But most of the work I'll talk about today is work that I did during my PhD at Penn State with Mike Janik and Mike Hickner, and during my postdoc at Leiden University in the Netherlands with Mark Coper. And so before I get started into kind of the specifics, first just tell you a little bit about why I am interested in electrocatalysis. I'm sure I don't have to convince anyone in this audience that renewable energy is good. We want more renewable energy. We want to make less greenhouse gases, fewer greenhouse gas emissions. And so I just want to present some information that I think is, at least to me, seems very positive. And so I want to show that the costs of renewable energy are declining significantly. So the figure on the left shows the cost of solar PV modules in dollars per watt over the last 40 years. And you can see the cost has dropped by over 2 orders of magnitude. And it continues to drop further today. So this is, I think, a really good thing, right, that we're dropping the costs. More importantly, this has also led to increasing utilization of renewable resources. So here now I'm showing the percent of electricity produced in the United States over the last 10 years from wind and solar. You can see these numbers are actually like measurable percentages of our total electricity production, and they're increasing. The most recent data I could find from 2017 shows we produced about 6% of our electricity from wind and a little more than 1% from solar. I've been told that, as of today, these numbers are even higher. And so I think this is really cool. To me, this is a huge change that we've seen over the last 10 years. But of course, we'd like to see this, become an even larger percentage of our total electricity production. And at some point, to keep increasing our utilization of intermittent renewable energy, we will need energy storage, right? So we will need to be able to store that intermittent solar and wind power so that we can still produce electricity when the sun is not shining and the wind is not blowing. I think electrochemistry could be great at storing this energy. For example, we could store this electricity in batteries, but we can also use electrocatalysis. For example, we could take this renewable electricity and split water to make hydrogen and store that electrical energy in hydrogen fuel. Or we could, for example, take organic molecules derived from biomass and use electrocatalysis to upgrade those to make valuable, renewable fuels and chemicals and feedstocks for the chemical industry. And so I'm pretty much interested in everything shown on the right-hand side of this slide. But most of my work has been focused on understanding electrocatalysis at a very fundamental level. How does the structure of the catalyst and the composition of a catalyst correlate with activity, selectivity, and stability in the electrochemical environment? And how does the composition of the electrolyte affect reaction activity, selectivity, and stability? And so I will be focusing in this talk today on electrolyte effects, in particular on the effects of alkaline metal cations in electrolyte pH. And I think when we talk about cation effects, one of the most obvious and most widely discussed examples of that is looking at the effects of cation identity on CO2 electroreduction. So CO2 electroreduction, we take carbon dioxide, we add protons and electrons to try and turn it into valuable fuels and chemicals, closing the carbon cycle. If we look at just the bottom half of this figure here, this is showing CO2 electroreduction on copper. We can see that the rate of this reaction, given here as the current density, depends on the cation that is present in our electrolyte. Right? It's highest with cesium and lowest with lithium. Maybe even more excitingly, the selectivity is also significantly affected by the cation present in our electrolyte. If we look in particular at ethylene, shown here in purple, we can see that we have a much higher selectivity to ethylene with cesium, actually 21 times higher selectivity with cesium in our electrolyte than with lithium in our electrolyte. And so if we want to produce ethylene, or if we want to produce some particular product, we can tune electrolyte composition to increase activity and selectivity, but we need to understand the mechanisms of this effect to really take advantage of it. So this is something we want to understand at the atomic scale. Something that I've been interested in studying for the last few years is looking at the pH dependence of the hydrogen oxidation and hydrogen evolution reactions, where it's found that on many active catalysts, the rate of both of these reactions is significantly slower in an alkaline electrolyte than in an acid electrolyte. This is shown on platinum, polycrystalline platinum in the figure on the left here, where we have the overpotential, or the driving force to drive hydrogen oxidation forward, versus the rates of the reaction. And we can see that at any given potential, any given driving force, the rate is 2 to 3 orders of magnitude higher in the acid electrolyte shown in red than in the alkaline electrolyte shown in black. Right, so this is a huge effect. We'd really like to understand, why electrolyte pH has this big effect. We think we can make, less expensive alkaline fuel cells than our very expensive acid fuel cells, but to do that, we need to keep the high activity that we see in acids. So we really want to understand, how does pH cause this effect? I'll just briefly mention, we see a similar effect on hydrogen evolution, and in particular, we see this even at very high pH. And so here, again, we're showing the reaction rates, and you can see at any given potential, the rate is lowest at pH 13 than it is at pH 12 or pH 11. And so we really want to understand, what is the effect of pH? And so we might ask, what can change when we change electrolyte pH? Right? First, we could see that we can change the proton donor. Right? If we have a simple electrolyte, we might first switch from having H3O plus as our proton donor in acid, or water as our proton donor in an alkaline electrolyte. And maybe the kinetics of pulling a proton off of either of these molecules is different. And so recent work out of the SunCat and CAT theory groups showed that this is exactly true for hydrogen evolution on platinum, where the barrier to pull a proton off of water to stick it on a platinum surface is much, much lower, almost barrierless, than it is to pull a proton off of water, which is what we would have at high pH. So this seems to explain, the majority of this huge effect of pH on reaction kinetics. However, I'll mention it doesn't, as of yet, explain this shift that we see with pH, even when we, know we already have just water as a proton donor. So here we already have, pure water as a proton donor. And so we might ask, what else could affect, what else changes when we change electrolyte pH? And so we know that we also change the electric field across the surface. So how does this work? So if we look at the figure on the right here, I'm showing the electrochemical potential scale versus what's called the standard hydrogen electrode, which is given a potential of 0 when the free energy of hydrogen gas is in equilibrium with the free energy of protons at 1 molar concentration of protons, so a pH of 0. If we now look at this same reaction, but at pH 14, we've decreased the concentration of protons by 14 orders of magnitude. And so that also causes a shift in the equilibrium potential for this reaction by, minus 0.83 volts. So why is this important? Well, as far as we can tell, the potential of 0 charge of an electrode surface is independent of pH. This potential of 0 charge, or PZC, is the potential where the electric field across the surface is 0. And so sticking with platinum, this is known to be, the PZC of platinum is somewhere around 0.3 volts on the scale. And so what this means is, if we carry out, hydrogen evolution or hydrogen oxidation in an acid electrolyte, we're much closer to the PZC than we are if we carry out those same reactions in an alkaline electrolyte. How far we are from the PZC determines the magnitude of our electric field. And so if we go from acid to base, we're going to have a much larger electric field and also a much higher concentration, in this case, of cations close to our electrode surface. Similarly, we might also ask, if we have this high concentration of cations close to the surface, could they also somehow affect reaction kinetics? To be different from the electric field effects, then we might ask, could it become favorable when we have this high cation concentration at high pH? Could it be favorable for some small fraction of these cations to sit close enough to the surface that they give up some of their solvation? We're going to call this for now ion or cation adsorption, but we'll talk more about what this really means later on. We don't necessarily need electron transfer. We're just saying they sit close enough to the surface to give up some of their solvation. And this is important because if they did that, maybe they might then interact directly with various reactive intermediates that are absorbed on the surface. And I'll mention that the electric field across the surface could affect the adsorption energy of these reaction intermediates, could affect activation energies for various reactions occurring on our surface, as can the presence of a partially desolvated cation sitting close to these species on a surface. And so most of the work we'll talk about today is really trying to understand, is this possible? And if so, what effects does it have? I'll just mention briefly, we could also have some combination of all of the above. I only point that out because then things could get really complicated, right? You can see here, one of our proton donors is charged. And so the concentration of this particular proton donor, might be, close to the surface, might be field dependent, right? If we have a higher electric field, maybe we'll increase our concentration of proton donor. And so these things can rapidly become very complicated. For the rest of the talk, I'm going to focus just on adsorption thermodynamics. I won't actually take the next step into explaining how that relates to catalysis, but that is the goal of our work. We kind of want to first understand how can pH and electric fields and cations close to the surface affect the thermodynamics of adsorption of reactive species. That then might explain, how the pH and cations affect the rate of an electrocatalytic reaction that involves that reactive species. And so to this end, one of the first examples we'll talk about is understanding adsorption on polycrystalline platinum and how that changes with pH. And so here I'm showing cyclic voltammograms measured on a polycrystalline platinum electrode. Just very briefly, in a voltammogram, what we're doing is we're controlling the potential of our working electrode, in this case, a hunk of polycrystalline platinum. As we vary the potential, we're driving various reactions which involve electron transfer to become favorable. Different reactions become favorable at different potentials. And when those electron transfer reactions transfer electrons with our surface, we measure that as a change in the current. And so I realize that this kind of looks like a mess here. There are CVs measured on polycrystalline platinum in different in electrolytes with different pH. There are two sharp peaks that are known to be seen at low potentials here. And we see that those sharp peaks shift more positively with increasing pH. And so that's highlighted in this figure on the right here. They shift roughly linearly with increasing pH. I'll mention we've already accounted for kind of the expected thermodynamic shift we would see with pH. And so this is truly an anomalous shift beyond what we would expect from standard thermodynamics. And so we might ask, what is going on in these peaks? We know it's an adsorption reaction. We also know it's adsorption on stepped sites on the polycrystalline platinum electrode, in particular 110 steps and 100 steps. It was traditionally assumed that this corresponded to hydrogen adsorption. We'll show actually that it's not. And so we want to identify what is going on in these peaks. Why do they shift with pH? And is that somehow related to the presence of a cation sitting close to the electrode surface? To give you kind of an outline for the rest of the talk, as well as some spoilers, we will show that these peaks correspond to an exchange between adsorbed hydrogen and adsorbed hydroxide and water on these platinum step sites. We'll show that they shift with pH due to the close approach of a cation, an alkali metal cation, to the electrode surface, which then interacts with adsorbed OH and water along the step. We'll then show that we can extend this same concept to explain the effects of pH on hydroxide adsorption on flat platinum surfaces, not just on steps. And something I'm really excited to show is we actually find an alkali metal cation that interacts a cation, it's not actually an alkali metal cation, a cation that interacts so strongly with adsorbed hydroxide on platinum that it produces cation hydroxide islands on the electrode surface. If I still have time, then at the end of the talk, I'll very briefly discuss some additional kind of indirect experimental evidence we have for this kind of cation adsorption and make some comments about how to model solvation in density functional theory. And so to answer these questions, we're going to use a combination of density functional theory and experiment. Just very briefly on the DFT side, we're gonna, we wanna calculate adsorption thermodynamics. We can do this relatively simply with DFT. I won't go too much into detail about how we do this, but if anyone has any questions, please, ask those at the end. I'd be happy to talk about this. But basically, we have some, generic adsorption reaction shown on the top of the slide here. We can use DFT to find the free energy of each of our reactant and product states, and use that to calculate the free energy change for adsorption. That's just the free energy of the products minus the free energy of reactants. And that delta G will tell us when that reaction becomes favorable, at what concentration of species in solution and at what electrode potential. Typically, what I'll show in the talk is actually not delta G as a function of potential. Instead, I'll solve for the potential that gives us a delta G equal to 0 and call that our equilibrium adsorption potential. Just very briefly, we have to keep in mind this is all occurring in the electrochemical environment. And so we need to be thinking about how solvation affects the thermodynamics and how electric fields can affect the thermodynamics. For our solution phase ions, we have kind of thermodynamic cycles we can use to calculate the free energy of the species without ever having to actually solvate an ion in DFT. And so I won't really talk about that because we have ways to get around it very accurately. We do need to consider how to model solvation near the electrode surface. For most of what I'll show, we will use a small number of explicit water molecules hydrogen bonded to our adsorbate to consider the effect of solvation or approximate the effect of solvation on adsorption. And I'll give some comments throughout the talk about whether we think this is a realistic or accurate approach or not. Okay, I'll then also briefly mention that in the DFT, we're not going to directly model a polycrystalline platinum surface, and I should say in the experiment with polycrystalline platinum, we don't know what our surface structure looks like. And so to really understand what's going on here, we're going to make comparisons between DFT and measurements on what are called single crystal electrodes. Right? It was measurements on single crystals that allowed us to understand that these sharp peaks measured at low potentials on platinum actually come from adsorption on step sites, because we only see these peaks when we use a stepped surface. And so we're going to use DFT to look at adsorption on the steps and terraces of the platinum 553 surface, as well as on the platinum 533 surface, which have the two different step sites, whose adsorption peaks we were seeing in the polycrystalline platinum. The added benefit here is we can directly compare our DFT to experiment, and we know from experiment exactly how many of these sites we have on the surface. We know exactly the geometry of our surface. And so first, because these step peaks were assumed to involve hydrogen adsorption, that was the first thing we looked at with DFT, right? We calculated the adsorption potential for hydrogen onto the terraces of these two stepped platinum surfaces shown in blue here, as well as on the stepped edges shown in red and in green. I should say briefly, this is ignoring the effect of near surface solvation on the adsorption of this hydrogen. We'll come back to that in a few slides. So the first thing we can see is that adsorption on the steps is much stronger than on the terraces. We might expect this because the stepped platinum atoms are under-coordinated, so they should bind most adsorbates more strongly. But what's kind of concerning is if we now compare this adsorption potential for hydrogen on the steps to experiment. So here I'm showing again, the CVs measured experimentally on platinum 553 and 533 in an acid electrolyte, compared to our DFT predicted adsorption potentials for hydrogen on the steps shown with these X's here, these crosses. We see that they are far more positive than what's observed experimentally, right? And so I think experimentalists might look at this and say, okay, well, DFT sucks. It's not useful here, right? We get wrong numbers. But we can do better than that, and we can try to understand why did DFT get this wrong. And what's interesting is that if we compare our energetics to the adsorption of hydrogen on stepped platinum in the ultra high vacuum environment, then we do match those thermodynamics. And so I'm not showing that here, but just trust me that we match what's measured in ultra high vacuum. And so that would tell us that it's not really the DFT that's wrong, it's that we're missing something that's going on in the electrochemical environment that's different from ultra high vacuum. And so we could ask, well, what could possibly be different about the electrochemical environment? I think the most obvious answer that most people think of, at least people that study electrochemistry, is that, of course, we have solvent present near our electrode surface. These water molecules could interact with our adsorbate and promote its adsorption, weaken its adsorption, somehow interact with that I'll briefly mention that there are other ways that solvent can affect our adsorption energetics that we also need to consider, and I'll hopefully show are actually even more important in some cases than this kind of traditional solvating effect. The first is that we have to consider solvent adsorption. Maybe water binds very strongly to the platinum step edges, and so hydrogen to adsorb needs to displace that water. That would then affect the adsorption energy that we measure experimentally for hydrogen in the electrochemical environment. It would be convoluted with the adsorption energy of water. And we should also consider solvent decomposition. When we measure a CV in an aqueous electrolyte, we see an adsorption peak, but we cannot determine whether that adsorption peak is coming from hydrogen, hydroxide, or oxygen, basically any decomposition product from water from the voltammetry alone. And so we also have to consider that maybe that peak involves hydroxide adsorption or oxygen adsorption. And so we've looked at all of these options with density functional theory. And what we found is that we needed to consider solvent decomposition. What we find is that the stepped platinum sites not only bind hydrogen very strongly, but also bind hydroxide very strongly. And so what I'm showing here, the end of each of these bars represents the equilibrium adsorption potential for hydrogen and for hydroxide. Because hydrogen adsorption is a reduction reaction, it becomes more favorable as we go to potentials lower than that adsorption potential. As hydroxide adsorption is an oxidation reaction, it becomes more favorable as we go to more positive potentials. We can see that here if we plot the delta G versus potential. The equilibrium potential basically represents where this delta G crosses zero. And what we see on the platinum steps, at least if we consider co-adsorbed water with that hydroxide, is that these two curves overlap. And so now the peak that we measure in the CV is not going to be where hydrogen adsorbs. It's going to be where we see this exchange between adsorbed hydrogen and adsorbed hydroxide in water. And so now if we simulate cyclic voltammograms considering this exchange, we find that they do in fact now match experiment. And so here we see a broad peak for adsorption on both surfaces that's due to hydrogen adsorption on the terraces. I didn't really talk about that, but that matches experiment quite nicely. But now we can see if we consider this exchange between adsorbed hydrogen and adsorbed hydroxide and water on the step, now we can capture much more accurately the location of these step-associated peaks, right? We're not shifted way more positive of what's seen experimentally. We match them very nicely. And so now we can explain the difference between the adsorption we saw in the ultra-high vacuum and in the electrochemical environment is that in UHV, we can adsorb hydrogen on its own, and in water, we have this exchange on the steps between adsorbed hydrogen and co-adsorbed OH in water. What's very important to mention here is we only can capture this binding strength accurately because we considered the effect of co-adsorbed water on hydroxide adsorption. If we look at the difference between the green bars here and the blue bars here, the green is for OH with hydrogen bonded water. The blue is just for OH basically on the surface in vacuum. What we find is that when OH adsorbs in vacuum, it transfers, basically all of its charge. And so it sits neutral to the surface, generates a negligible surface normal dipole moment. But we have to keep in mind hydroxide has its own internal dipole moment, which makes it very favorable for water to co-adsorb with that hydroxide on the step. And when it does, it forms these strong hydrogen bonds, and that promotes hydroxide adsorption relative to what we find in vacuum. And notice that the trend in which surface binds OH more strongly is different whether we ignore that effect of solvation or include that effect of solvation. And so for OH, we needed to consider solvent decomposition and this kind of solvating effect. Importantly, once we included the co-adsorbed water, we matched experiment pretty well. We didn't need additional water above the surface to capture this effect. And so now we know what's going on in these step peaks. We still need to explain why they shift with pH. And so again, we wanted to study whether or not the alkaline metal cation could sit close enough to the surface at high pH that it would interact with various adsorbates on the surface. And we find that that's exactly what happens. We find it's favorable for an alkaline metal cation to sit close, especially to the step edge of a step platinum surface. We call this specific adsorption. We say that it's favorable. Again, we'd see only minor amounts of electron transfer, so we would never see an adsorption peak for this in a CV. Really, what we're saying here is it sits close enough to the surface to give up some of its solvation. It sits too close to the surface for water to be in between the cation and the surface. Further, once we put it there, we find that it has a big effect on the adsorption energy of hydroxide in water. Basically, because this cation does not transfer an electron, it retains most of its positive charge, and it kind of tries to steal the solvation from this adsorbed hydroxide, and it disrupts the strong hydrogen bonding between the co-adsorbed hydroxide and water on the step edge. And so now when we calculate the potential to go from a hydrogen covered step to an OH and water covered step, that's shown in blue here, we can see for both step types, the presence of an alkali metal cation, in this case sodium, shifts that peak to more positive potentials. And so now, and that's exactly what we see when we increase the pH experimentally. And so now we can simulate CVs again, considering now the effect of the cation. Here we have the dashed line as the CV experimentally measured for platinum 553 and perchloric acid. The solid line is the CV experimentally measured on that same surface in sodium hydroxide. Again, what I've already shown previously, we can match the CV in acid with DFT. And now if we consider this effect of the cation coming close to the step and weakening OH and water adsorption, we find that also matches experiment very nicely. And so this seems to support that our hypothesis was correct. The cations can sit close to the surface, and once they're there, because they retain most of their charge, they interact strongly with adsorbed species like OH and water. But when we stick this cation close to the surface, because it retains most of its charge, that also generates a large surface normal electric field. And so we could ask, well, maybe this really was an electric field effect, and we've tricked ourselves by thinking it's a cation effect. And so this is where it's really nice to have additional insight from experiment. I'll say this is work that I did during my PhD with Dr. Janik. And it was around this time that we started collaborating with Mark's group before I moved there for a postdoc. And one of the students in his group, Xiaoting, performed a really interesting set of experiments that I think strongly supports and elucidates the important role of the alkali metal cation. And so the first thing that she did is she measured cyclic voltammograms on platinum 553 in varying pH electrolytes without adding the presence of an alkali metal cation. So how do you do this? You take a strong acid and you dilute it. And what she finds is when you vary the pH without adding an alkali metal cation, the peak does not shift. The step-associated peak remains at the same potential. And so there's actually 3 CVs here that all overlap on top of one another. And so this would seem to support that if we don't have the cation in the electrolyte, we don't see the peak shift. And this also suggests that since we're changing pH, this means we are changing the electric field across the surface. And this means adsorption in this peak shows no electric field dependence, at least from pH 1 to 3, at least over the small pH range. Once we add, so now we can, at pH 3, we can now add the presence of an alkali metal cation and see what happens. We find once we add the cation at pH 3, the peak shifts. More importantly, if we increase the concentration of the cation at constant pH, we see the peak shifts more. This would support we have a higher coverage of the cation along the step, we shift the peak more. Lastly, at the highest pH, we see that the location of the peak depends on the cation identity. So we see a smaller shift with lithium and a higher shift with sodium, potassium, and cesium. So it depends. Here we're looking at constant pH, and we see the identity of the cation has an effect. And so this seems to support that this effect of pH is really an effect of the cation sitting close to the surface, which becomes increasingly favorable with increasing pH, and that weakens the adsorption of OH and water. And we can capture all of this with DFT. So now instead of just looking at no cation and a high coverage of cation, we can actually vary the coverage of the alkali metal cation and show that that allows us to capture the continuous shift of this peak with increasing pH. And so this black square here, diamond, is the location of the peak in acid. We're showing the experimentally measured potential versus DFT predicted potential. And we see that shifts positively with increasing pH. We find with DFT, this correlates with a higher coverage of cation along the step, and that shifts the peak more because it causes a greater weakening of OH and water adsorption. I will mention something very important to consider here, which is that the kind of absolute level of accuracy we see between DFT and experiment depends on a lot of things, right? If we used a different DFT exchange correlation functional, we'd get different potentials, and they would then fall, maybe further or maybe closer to this y equals x line. Importantly, we can show it also somehow depends on how we model solvation. And so I mentioned we've always used a small amount of explicit solvent. Here, what I'm showing is the DFT calculated step peak potential in the absence of sodium and in the presence of sodium for basically hydroxide adsorbed with a lot of explicit water and hydroxide adsorbed with less explicit water. What we see is these peak potentials are different. If we add more water, we get a different potential. And so this is something important to keep in mind. And so if we want to be truly, predictive in terms of the absolute value of that peak, that would be very difficult to do. What's important here, though, is what we wanted to understand was the effect of the alkali metal cation. And regardless of how much explicit water we include, we see the cation always has the same effect. It shifts this peak to more positive potentials. Further, we can even add on an implicit solvation model on top of this. And we see, again, the cation still has the exact same effect. It weakens OH and water adsorption, at least for low OH coverage, and shifts the peak to more positive potentials. I'll just briefly mention that we can use kind of the same understanding we developed on the step sites, the same mechanism to explain the effects of pH on hydroxide adsorption on platinum-111. It's just the effects on this flat platinum-111 surface are a little bit more subtle than what we see in terms of the effects of pH on the step sites. And so here we're showing CVs measured on platinum-111 in perchloric acid, that's the dashed line, and in sodium hydroxide, that's the solid line. We kind of knew already that this high potential peak corresponds to OH adsorption through lots of work from other people over the years. We can also test this with DFT. But we can see when we increase pH, what we're doing here is we're weakening low coverage OH adsorption and strengthening higher coverage OH adsorption. This is exactly the same phenomena that we saw in terms of the effects of pH on the step-associated peak. I didn't mention it. We actually also see a slightly higher coverage of hydroxide adsorbed in an alkaline electrolyte. And so the cation weakens low coverage adsorption. That's why the peak shifts, can also slightly promote high coverage hydroxide adsorption. And so we can model this also on the flat platinum-111 surface, just like we did on the step sites. And we find, again, roughly the same picture, that the presence of the cation weakens low coverage adsorption. So the blue points are the OH adsorption potential as a function of OH coverage without a cation, and then with a sodium cation, we see the sodium cation weakens low coverage adsorption, strengthens high coverage adsorption. Really, the only difference with the flat surface is now we have to pay very close attention to the coverage of the cation that we're considering. What we find is if we really want to approach being quantitative with these methods, we have to consider that different cations can adsorb to different coverages on our platinum-111 surface. And so that coverage not only explains the effect of pH, but also differences between the cations. So this red line now considers the most stable sodium coverage adsorbed on the surface. At high OH coverages, we get a mutual attraction between high coverage OH and the sodium cation close to the surface, which allows us to achieve a higher sodium coverage, which explains this even more significant promotion. Again, the general trend matches very well with experiment and can explain why we see an increased coverage of hydroxide in the alkaline electrolyte relative to the acid electrolyte. Again, this peak shifts because the cation weakens low coverage adsorption, and we increase the coverage because the cation also promotes high coverage adsorption. Just very briefly, we can also explain some of the identity effects. I won't talk too much about this, but it also comes down to the relative coverage that we can achieve on the surface of these various alkali metal cations. What I think is more exciting, I want to move on to the kind of last thing, the last at least set of results I'd like to talk about here, which is looking at a cation that we find interacts so strongly with adsorbed hydroxide and platinum-111 that it actually causes island formation on this surface, causes hydroxide island formation. And so we looked with DFT at the effects of cations other than the alkali metal cations. In particular, here we're showing work looking at beryllium. Beryllium is one of the smallest cations, has a higher charge to size ratio than lithium. And we see that gives it a larger promoting effect on high coverage OH adsorption than lithium does. So if we have a little bit of beryllium on our surface, we promote OH adsorption a little bit. Again, kind of similar to what we saw here with lithium that I went through very quickly. If we have a higher coverage of beryllium, we can promote high coverage OH adsorption significantly by 0.3 volt shift here. What's interesting is if we now compare this to experiments, so these are voltammograms previously measured on platinum-111 in 0.1 molar sodium hydroxide in black and 0.1 molar sodium hydroxide containing trace amounts of beryllium in red. You can see in the forward-going scan, there's a huge shift, or I shouldn't say huge, but a fairly large shift to lower potentials of this OH adsorption peak. That says beryllium does promote hydroxide adsorption. We can compare this to what we see with the alkali metal cations, and it does promote it a little bit more than lithium. But what's very interesting is then if we look at the reverse scan, where we scan negatively. We do not see this peak. We do not see hydroxide desorption at the same potential where we saw hydroxide adsorption. It's shifted to much lower potentials. And so I think this is really exciting because this could support that when we complete the OH add layer at high potentials, it becomes favorable to absorb a higher coverage of beryllium, and that stabilizes this add layer down to very low potential. And so we wanted to investigate this further, trying to determine if this is really what was going on. I think any experimentalist would look at this CV and say, this peak splitting is due to kinetics, not thermodynamics. Typically, when we see a hysteresis or a peak splitting in a peak, an absorption peak between the positive and negative going scans, our first thought is that that corresponds to slow kinetics. Basically, we're scanning the potential at a faster rate than the rate of our reaction. And so we're not really giving the reaction enough time for the species to adsorb and desorb. If we slowed down the scan rate, these two peaks would come together. And so what I did is I then, repeated these measurements in platinum 111. So it's shown on the left here. And then I measured CVs as a function of scan rate. And if this were due to kinetics, the peak in the forward going scan and the negative going scan should move closer together. There's kind of a lot of things that are changing here, but importantly, we do not see these two peaks come closer together. And that's maybe a little bit easier to see if I plot the potential of the peak. So the blue points are the potential of the peak in the positive going scan. The orange are the points in the negative going scan. And what we can see is that they do show a slight dependence on scan rate, but it's not large. And these two lines do not intersect. If really this was only a kinetic effect, these two peaks at the slowest scan rate should be at the same potential, and these two lines would intersect at the same potential. And you can see that they don't. What does change when we change scan rate is the relative amount of charge in this peak in the negative going scan. And you can see as we scan faster, this peak at low potentials has less charge in it, gets smaller, and this peak at high potentials starts to grow in. And this peak at high potentials does line up with the peak in the positive going scan, which actually says this process becomes more reversible if we increase the scan rate. And so this really says it's not a kinetic effect. And I think the only explanation for this is that instead it is a thermodynamic effect. And so what do we mean by that? So I showed briefly some DFT results. I'll show more in a few slides, showing that if we have a low coverage of beryllium that promotes a low coverage of hydroxide adsorption, relative to no cation or relative to a sodium cation. Once we finish this add layer, though, it becomes favorable to adsorb a higher coverage of beryllium into the add layer because we have mutually attractive interactions between the adsorbed beryllium and the adsorbed hydroxide. Further, if we scan slowly enough, what happens is this add layer of high coverage OH and high coverage beryllium actually reorganizes and forms islands on the surface where locally we have a very high coverage of beryllium and high coverage of hydroxide that is very stable because of these mutually attractive interactions between the adsorbed beryllium and adsorbed hydroxide. And so effectively what we're seeing here is what we would call a first order phase transition, which is not commonly seen in electrochemistry. We see second order phase transitions. That's the sharp peak that we see in the OH adsorption peak on platinum 111 in acid. And so this is actually a first order phase transition where, again, the beryllium makes the interactions between adsorbed OH so attractive that we form islands of hydroxide on the surface that are more stably adsorbed. And so they don't desorb until we go to much lower potentials. And so we can also see this instead of by varying the scan rates, if this is really what's going on, if we really have island formation, we can study the kinetics by just holding the potential at this upper potential limit for varying amounts of time and then scanning negatively very quickly. And so that's what I'm showing here. We held at this upper potential limit for between 0.1 seconds and 100 seconds. And what we can see, and then we scanned negatively very quickly. What we can see is for the shortest times shown in red, we see most of our charge for our hydroxide desorption occurs in this first peak here, which matches roughly with the location of the peak we see in just pure sodium hydroxide, so no effect of beryllium. Remember, we have only kind of a trace concentration of beryllium in our electrolyte. And the majority of our charge then appears in this second peak. And I'm not showing it, but the potential of this peak lines up very nicely with the peak that we see in the forward going scan. Meaning that if we scan very quickly, we don't have time to form these islands and our peak is reversible and we just have this slight promoting effect of a low coverage of beryllium on hydroxide adsorption. However, as we increase the amount of time that we hold the electrode at this high potential, we give more time for these strongly bound beryllium hydroxide islands to form on the surface. We get this first order phase transition and these high potential peaks disappear. And most of our hydroxide is then stuck on the surface down to very, very low potentials, actually overlapping with even hydrogen adsorption. And so we have to start absorbing hydrogen on the surface to start kicking off the hydroxide. And so I think, and I'll just briefly show, we have lots of DFT data. I'm not going to show all of it here. We've also used DFT to examine these interactions. I'll just show, we can look at the adsorption of hydroxide on this surface. So we calculate the hydroxide adsorption potential just at one particular coverage of high hydroxide coverage as a function of beryllium coverage on the surface. And we see a strong promoting effect. So beryllium strongly promotes OH adsorption on the surface. And we can look at the beryllium adsorption potential as a function of OH coverage and see we also have a promotion of beryllium adsorption with increasing OH coverage. Again, what this means is that we have mutually attractive interactions between beryllium and hydroxide that leads to this island formation on the surface and this hysteresis that's observed in the voltammograms in this first order phase transition. And so why is this important? Just briefly, it would be kind of hard to explain these effects as being due to the effect of an electric field. And so it strongly, at least to me, supports that we have to have this beryllium cation sitting very close to the surface such that it can directly interact with the absorbed hydroxide to form these beryllium hydroxide islands. And also we could now consider how might this affect electrocatalysis, right? Adsorbed hydroxide is a reactive intermediate in many electrocatalytic reactions. And so presumably this could have a significant effect on the rates and selectivities of reactions that involve adsorbed hydroxide. And we could also look that, maybe beryllium also affects the adsorption of other reactive intermediates on our surface. Okay, I'd like to finish in a couple minutes, so I just want to very briefly make a couple comments. And first, I just want to mention that, I think some people tend to think that cation-specific adsorption is impossible because we have never observed direct experimental evidence for cation adsorption. So what do we mean by that? We've never seen, an adsorption peak in a CV that correlates or that corresponds to the adsorption of an alkali metal cation. We see hydrogen adsorption, hydroxide adsorption. We see the effects of a cation, but we never see a peak that we could really assign to being due to the cation. And so again, what we're saying here is that maybe we don't have significant electron transfer. And so we don't see it in the CV, but that doesn't mean the cation can't still sit close enough to the surface that it gives up some of its solvation. And I think there's lots of experimental evidence that kind of indirectly supports this idea. Just very briefly, there's a lot of radio tracer studies from the 70s and 80s, mostly from researchers in the Soviet Union, where they use radioactive isotopes of alkali metal cations to directly measure their coverage on the surface independent of the voltammetry. And so here we're showing coverage versus potential of a cesium cation at pH 3 on, I believe, yes, a platinum electrode. And so we can directly measure this coverage and see that it increases with decreasing potential. This could just be cations in the double layer. It doesn't tell us where these cations are. So we could look to X-ray scattering experiments, which can actually measure the distance between a cation and, for example, a platinum electrode surface in situ. And we can see that for at least the cations that have been observed so far, they sit too close to the surface for water to sit in between the ion and the surface. And that's exactly what we're claiming we see with our DFT. We can also look to nanogravimetry. We can measure the change in mass of our electrode as a function of potential to see with very heavy cations like cesium, we see a big change in mass. And I think what to me is maybe one of the coolest experiments is we can look at STM imaging of a cyanide add layer on platinum 111. Cyanide binds very strongly to platinum, forms a well-ordered add layer. And it also interacts very strongly with potassium in solution, such that potassium specifically adsorbs, and these bright spots actually correspond to potassium on the surface in the cyanide add layer that we're seeing with the STM. And the only way we would see the cation in the STM would be if it's bound so strongly to the cyanide or to the surface that it's not, rapidly diffusing around, which would just show up as noise in the STM. One other comment that I'd like to make very briefly, is I think we need to think very critically about how we model near surface solvation. There's many different ways to model the effect of solvent near a surface. We could totally ignore it and just model things in vacuum, or we could add, hundreds of water molecules and look at their dynamics with ab initio molecular dynamics. And there's lots of, methods in between. And I think roughly they follow this order of computational intensity, right? Certainly modeling things in vacuum is the easiest, and doing molecular dynamics of hundreds of water molecules near a surface is hardest. But I get the impression, maybe I'm wrong, but I get the impression that our community tends to assume that accuracy also follows this same trend. And certainly it might, but I don't think there's evidence yet to really say that this is true. And I think instead of assuming that by putting more effort into the computational modeling, that by using more complicated models, we will necessarily become more accurate. To me, this is a question that we need to answer, right? Instead of trying to capture effects on electrocatalysis or trying to study electrocatalysis directly, we need to also devote some time into studying what is the effect of water near a surface, what is the behavior of water near a surface, and what is the best way, most accurate way to model that for a given electrode, a given electrolyte, a given set of conditions. I'll just mention briefly, I think we can model hydrogen adsorption on platinum in vacuum and can match experiment very well when we don't see competition from water adsorption or water decomposition. And so we can then totally ignore solvent near the surface and be very accurate with a model in vacuum. And I bring this up because each of these methods has limitations. And yes, it could be that these more computationally intensive methods are more accurate, but they are not free from limitations, and we always need to consider how these limitations affect our choice of model. The last comment I want to make is just the behavior of water. We should keep in mind the behavior of water near an electrode surface is very different than it is for bulk water, right? For bulk water, we imagine lots of water molecules all moving around at 300 Kelvin. We can form these, long time scale, long length scale, hydrogen bonded structures. But in the electrochemical environment, water near a surface tends to be far more ordered than bulk water. Here we're showing experimentally measured X-ray scattering measurements of the oxygen distribution function for water near a silver electrode surface. And we see these very sharp peaks within a few angstroms of the electrode surface, showing that water is more ordered, right? It has a higher peaks in density than bulk water. There are also measurements that show the dielectric constant of water is much lower near a surface. Now here, these are experiments not measured on a metal electrode, but instead on, I think, semiconducting boron nitride. Basically, they measured the capacitance of water between two layers of boron nitride and varied the height between, the spacing between these layers. And they fit this dielectric data with a model that says bulk water, in between these two layers has its bulk dielectric constant, but there's some layer near the surface about 7.5 angstroms in width that has a much, much lower dielectric constant. And it's interesting that this length scale corresponds very nicely with where we see this ordered water on an actual electrode surface in situ. And so again, we don't know what the dielectric constant of water is, next to a platinum electrode, next to a silver electrode, but I think there's lots of evidence to say it is much, much lower than what it is for bulk water. And so we really need to think about how this structure, how the dynamics, how the dielectric properties of water are different near a surface relative to that of bulk electrolyte. And so I'll conclude just by kind of summarizing. Hopefully I've convinced you we've shown that these step-associated peaks on platinum measured in electrochemistry correspond not to hydrogen adsorption, but an exchange between adsorbed hydrogen and adsorbed hydroxide in water, that they shift to more positive potentials with increasing pH due to the adsorption of a cation, which weakens OH and water adsorption on the step. And that's in some cases, we actually see such strong cation hydroxide interactions that they lead to island formation on the surface. With that, I'd like to briefly thank everyone in the Janik and Hickner and Cooper groups that I've had the pleasure of working with over the last few years, all of my funding sources over the last few years, as well as give a shout out to the students that have joined my new group at Clarkson University. So thank you to all of you as well for listening, and I will gladly take any questions. Thanks.
Okay, great. Thank you so much for that really fundamental talk. I'm sure that we will have lots of questions, and Nitish, I think we'll start to triage. Thank you.
Yeah, thanks a lot, Ian, for the great talk. So you can either post your questions or type X. So I already see there's a question from Vanessa, so you can unmute yourself and then ask the question.
Okay, hi. Thanks, Ian. That was really, really clear. And I'm really sorry if I mentioned this. This is a very basic question. In thermal catalysis, we talk about alkali metal promotion effects on the basis of dipole interactions. Is this what you're suggesting also here? I think you kind of implied it when you talked about the different charge densities and sizes, but
Yeah,
I'm not sure if you meant that or rather just the blocking of sites at the steps.
sure. That's a very good question. I'll say no, it's not a site blocking effect. We haven't really put a lot of effort into deconvoluting exactly how this interaction occurs between the cation and the adsorbed hydroxide in water, but I would expect it's mostly electrostatics. And the idea is that it's really this close approach of the partially desolvated cation that can interact very closely and very strongly with the adsorbed OH in water. So it's kind of a complex 3D electrostatic field. So it's exactly the same as what we see in heterogeneous gas phase catalysis with these kind of dipole effects. Really very similar.
Okay, thanks.
Maybe if I can just add very briefly, I will just say we do need to include the effects of water. If we model the effect of the cation on hydroxide adsorption without any water, we get a totally different effect. It's promoting. And so if we had, for example, high coverage OH in UHV without any water, we might see a different effect. So it's really disrupting this interaction between the OH and water that's absorbed on the surface.
Maybe I can follow up on that. So I think in your presentation you made a differentiation between cation and field effect.
Yep.
So is the promoter effect not also a field effect, or is there something different?
Well, so you mean the promoter effect in heterogeneous
I guess,
catalysis? Or?
I mean, I guess, so you have this additional disruptive water effect. Is this what it is?
Yeah, so it's I guess there's a couple ways to look at it. The picture that I would give is, if I compare this picture here with this picture here, right? With this picture here, we're going to have some fairly uniform electric field across the surface, right? It's going to be dictated by, pH and concentration of the cations, thickness of the double layer, all that stuff. However, when we look at this close approach of the cation, I would now imagine that the local electric field close to the adsorbate is now much more complex because these cations retain most of their charge on adsorption. And so it is an electrostatic, I expect it's mostly an electrostatic effect. But it's, to differentiate it from the field effect, I would say it's really this local 3D field effect as opposed to just the 1D or 2D field across the surface. And so why we consider that is because we know if we change the pH without a cation, the peak does not shift. And so when we change pH without the cation, we're still changing the electric field across the surface. But we can see, at least over this pH range, at least over some small range of changing electric field, we do not affect the binding of hydrogen and hydroxide in water on the step. It doesn't shift. And so this is kind of why we're viewing this effect of the cation as then being somehow slightly different from just the 2D field effect.
Okay. I mean, could it be an effect of just, I guess it's the same, we're saying the same thing, that either you think of it as a distance, so some sort of like closer ion surface distance, or a size effect, I guess.
So it's I think the distance is very important. I think the size is also certainly important because that's going to affect the
or it's like something to say the same thing. Yeah.
Right, and I'll say at some point we don't really know because we haven't really tried to deconvolute those things. I mean, we can show with like the beryllium, which is certainly smaller, we have much larger effects. But now if we're really forming these islands, maybe there is also some covalent interaction between beryllium and hydroxide. Maybe it goes beyond just electrostatics. We haven't tried to really piece that apart yet.
Okay, interesting.
Yeah, so I just wanted to ask with the identity of cations, can you like go back to this slide where you had the different cation and how there's a peak shift also with the cation identity?
Sure. So like with this here on the right?
Yeah, so this one, right? Yeah. So what are your thoughts on, so what is the difference between lithium and cesium here?
Yeah, so this is a very good question. And again, I would say we haven't pieced this, we haven't picked this apart in lots of detail.
Mhm.
In the DFT, we can capture this shift on the step by using a constant coverage of the cation and just changing the cation identity. And so if we model OH and water on the step with lithium versus sodium versus potassium versus cesium, we reproduce this shift that we observe experimentally. I expect, again, that the interaction is mostly electrostatic. Since they all have the same charge, probably it has to do with the size of the cation, right? That's going to affect the magnitude of the local field. But I can't point to some number that proves that. I'll add that on the flat surface, so this is kind of looking at, a one-dimensional kind of interaction. We're looking along the line of the step. If we look at the effect of cations on hydroxide on the 2D surface, so the 1,1,1 surface, I can say now, if we want to try and capture the difference between the cations, we need to consider the fact that they can absorb to different coverages. And now we have to consider that coverage effect on the surface. Lithium can absorb to a higher coverage. Why? Again, we haven't perfectly pieced that apart. I'm sure it has something to do with the size. Certainly there's a steric hindrance with something like cesium. We simply can't fit a lot of it on the surface and fit OH and water. So my guess would be it has to do with size in part, but we haven't really, I can't prove that.
Can I just add something to that? I'm sorry. I think in thermal catalysis, just looking at the effect of those, it is indeed a size thing in the sense that you can't fit that many altogether. Your cesiums are larger, so you can't fit that many. And that effectively then leads to a difference in the work function change, AKA perhaps a larger effective dipole overall. So that's why I was asking also originally whether this is just same as thermal catalysis, just dipole effects really.
Sure. Yeah, and again, I think in working through this, we've expected that there's some similarity with the promoting effects of cations and gas phase catalysis. But
although I do appreciate the extra complexity with the extra water dipoles.
Sure. Yeah, and we haven't made like a quantitative comparison to that, but I certainly there is overlap.
But I guess like one of the things is also, so the penalty for like a cesium to like lose its solvation conclu, that would be lower than for lithium, because lithium typically has a much larger solvation, right?
Yes, right. And so the solvation energy of the ions presumably also plays a role. I should say when they come to the surface, they're not fully desolvated. They lose some portion of their solvation, we expect. And so yes, certainly the solvation energy plays a role. The issue is with the cations we've looked at so far, the trend in cation size tracks with the trend in solvation energy. Because for the cation in bulk solution, at least the alkali metal cations, I mean, their size is what dictates their solvation energy, right? If they're tinier for the same charge, they interact more strongly with solvent.
Yeah,
but yes,
and
that's true.
I guess my last point is also, so the electrosorption valencies of these cations are also different, right?
Yes. And so we could then also say, beyond charge, maybe beyond the charge of the ion in solution, right? If they do transfer some small portion of an electron with the surface, maybe they take different charges on the surface.
Yeah.
We've also looked at that. Yeah. The degree of charge transfer is small.
Yeah.
0.1 of an electron, something on that order. If we add more solvation, that also decreases a bit.
Yeah.
But it is different. It is cation dependent. I don't have the results here, but we haven't been able to come up with a quantitative comparison. I think in one of the papers, I actually have a plot where we plot the surface normal dipole moment, which would be related to the electrosorption valency and the size versus the effect on OH binding. And there's a trend, but again, it's hard to interpret exactly what the cause of that trend is. So we're still trying to figure that out.
Great. Okay. We have a couple more questions. So there's a question from Sudarshan Vijay. Great talk. Do you see any hysteresis for other cations apart from beryllium on platinum, particularly for lithium?
So it's a very good question. So far, the answer is no. I will maybe briefly mention, let me see if I can go to the slide real quick. If we look at, one second here. I don't know if I have exactly, yeah. So, we do see some hysteresis in some cases on hydroxide adsorption in an alkaline electrolyte. Here, we see for adsorption on platinum 553 in an alkaline electrolyte, the step-associated peak actually shows some hysteresis. And so this is a kinetic effect. If we scan slower, these two peaks come together. We don't capture this in the DFT. We just look at thermodynamics of OH adsorption. I didn't show the simulated CVs for this surface, just for 553 in an alkaline electrolyte. But we just show a reversible peak. And you'll note that this is reversible in acid and less reversible in base because we're slowing down the kinetics of hydrogen hydroxide adsorption. But in terms of, you know, really a thermodynamic effect, a thermodynamic peak splitting, no, not that we've seen so far. For the alkaline metal cations, no, at least not anything that's, you know, large, significant, immediately obvious. I would expect there are other cations other than beryllium that would cause this. And so this is something I'm very interested in looking into, but we haven't seen this with any of the alkaline metal cations.
Great. So the next question is from Muhammad Azizullah. Thank you so much for the informative lecture. It would be great. It would be of great help if you could comment on DFT modeling with respect to the surface coverage of hydrogen or hydroxide or beryllium.
Sure. So thanks for the question. I'm not entirely sure how to answer that because I don't know how detailed of a comment you're looking for. So I can tell you, typically we're using a unit cell of a fixed size, and to vary the coverage, we're varying the number of adsorbates in the unit cell. And so if we want to vary the hydrogen coverage, you know, in a 3x3 platinum 111 unit cell, we're adding, you know, 1 to 9 hydrogen atoms to model 1/9 to 1 monolayer. I'll maybe mention this is particularly tricky when we model step surfaces, because if we want to look at coverage just along the step edge, you know, we need to use a wider step surface, and we drag around all of those terrace atoms. And so looking at very low coverages absorbed along the step gets tricky very quickly. But yeah, we just vary the coverage, and we've looked at, again, varying coverages of hydrogen, hydroxide, and of the cations. And we can calculate their adsorption energetics as a function of coverage on the surface. I'll say with beryllium, this is maybe particularly complicated because beryllium interacts so strongly with water and hydroxide that, you know, frequently we build structures that then turn into something else because we've reacted some of our water to make additional hydroxide on the surface. And so, yeah, there's a limit of how high of a coverage we can go with the cations. And maybe I'll briefly add, you know, hydrogen and hydroxide can adsorb to pretty wide range of coverage on platinum. All of the cation coverages we've looked at are all, you know, up to 1/3 of a monolayer. I think that's the highest cation coverage we look at, maybe slightly higher than that. I think we've gone up to 0.5 of a monolayer along the step. Because the cations retain most of their charge on adsorption, for all of the cations, they show very strongly repulsive interactions on the surface. And so that puts a, you know, hard limit on the favorability of adsorption with increasing coverage. So we see a strong coverage dependence, a repulsive interaction in the adsorption of the cations.
Great. We have a question from Federico. Great talk, Professor McCrum. Following up on the cation/field effect, did you quantify with DFT the local electric field generated by a cation close to the surface? In literature, it was quantified around 1 volt per angstrom, which I think is much larger than what you can get from just the potential. So cation generated field effect should be larger than applied electric potential effect locally, right?
So that's a very good question. In the simplest answer, I'll say we really haven't gone deep enough into that to know for sure. We can look at dipole moment changes on adsorption, and so we take that into account in our adsorption thermodynamics. It's kind of similar to looking at a change in work function on adsorption. And so we could kind of quantify that way the magnitude of the field, but really, to me, there's differences in this local field. And so we'd have to do a little bit more work than just calculating the dipole moment, the surface normal dipole moment, to see really what the local electric field looks like close to the adsorbate. And I'll add maybe that in DFT, I mean, we could apply whatever field we want. I mean, if we want to go much larger, we can certainly do that. Maybe in experiment, we're limited, but with DFT, we can apply whatever field we want. So I'm inclined to say I expect maybe we have a higher local field close to the cation than what we would see in, you know, typical electrochemistry experiments just based on the, you know, surface normal electric field, but we'd have to do more work to know that for sure.
I was, maybe, may I ask, like, how do you think we could quantify how local this is? Could you, for instance, kind of probe it with the adsorbate at different distances from your cation, or?
Yes.
Yeah.
So yeah, I think we should do that. I think, well, I have done it, but again, I don't really have anything overly insightful from that yet. But yes, I think that's one of the first things the easiest thing we could think to do would be, you know, especially on like the 111 surface, vary the distance between the adsorbate and the cation. And so we've tried that on platinum 111. Again, we don't have anything, you know, super insightful just yet. I'll maybe briefly mention, we did look at this a little bit on the step edge. And the hydroxide does not have to be close to the cation on the step to still see this weakening effect. But I think that's complicated because we get this long range hydrogen bonded structure of OH and water on the step. And so really what we're seeing is that if the cation is adsorbed anywhere along the step and it disrupts that water, it's going to alter this long range hydrogen bonded structure and alter the binding strength of OH and water. And so yes, maybe it's a little bit weaker, but it still is, you know, kind of fairly long range because the hydrogen bonding kind of distributes the effect of the cation. And so we'd have to kind of do a more careful study of, okay, let's just use kind of a local OH water structure and then just, yeah, move the cation around and see what effect that has.
Okay, no, that's really interesting. Yeah, no, I just had a thought. I was like, oh my God, maybe someone in thermocatalysis has at least done it for the simplest system, but
sure.
Okay, maybe then I can sneak in one last question if there's no one else. So it's actually right on the slide, this hysteresis phenomena. That's super interesting. Does it not also look like what happens when you sweep to higher potentials? Do you think that like this island formation is unique to what happens with beryllium? Or if you were to say sweep platinum to higher potentials and then you get what they call place exchange, all that jazz, like whether that's the same phenomena?
Sure. So that is a very interesting question. And I'll say maybe if we want to be super rigorous, there could be lots of things that are going on here. I think here we kind of went with the simplest explanation that can explain this hysteresis. But yes, if you scan the high potentials on platinum normally, you know, without beryllium, you'll see an oxygen, what we expect to be an oxygen adsorption peak, and there's a peak splitting. Typically because we assume oxygen adsorption kinetics are slow. But we do know this place exchange occurs. I've also done some work with some of the PhD students in Mark's group looking at the formation of surface oxides of platinum. And we see that above a certain critical oxygen coverage, it's favorable to start making kind of locally very high platinum oxygen coverage structures. So you actually lift platinum out of the surface and make a very high local high coverage of oxygen, which is kind of like an islanding of the oxygen on the surface. And so it could be that that's related. I think the difficulty there is we see that hysteresis even before we think we're getting this place exchange. And so it's hard to know, is the hysteresis just in the kinetics of oxygen adsorption, or is there also, are we also changing the surface structure by lifting up these platinums? The simple answer is yes, I think it certainly could be related. There's lots of interesting things we could do there, but it's hard to know for sure right now.
Yeah, we've been looking at platinum for decades, I guess.
Right. Yeah, I mean, I think a lot of my work, we're kind of realizing all these things are things we've studied for 100 years. And there's still new things we can learn. I think we're finding pH affects almost every reaction. Cations affect almost every reaction. So yeah, it's very interesting to try and explain these effects.
Yeah, definitely.
Can I ask one? Yeah, just one final question. So, apart from platinum, so are there other surfaces where you have these similar effects with OH adsorption and peak shifting with cations? And I asked this because if you go to surfaces that have drastically different PZCs, I guess the response would then be very different, right?
Sure. So that's also a very good question. The answer is yes. We haven't really looked too hard yet to see if, what role the electrode PZC plays. Certainly that would be important in figuring out, the coverage of cations near the surface. And so with these other metals, we haven't done anywhere near as, thorough of an investigation as we've done with platinum. But now that we think we figured this out with platinum, now we want to try and be predictive with the DFT on other surfaces. I'll briefly mention, yes. So we've seen kind of similar effects on other pure metal single crystal electrodes, and we're working on explaining those effects. Both effects where we see this exchange between adsorbed hydrogen and adsorbed hydroxide. So this is not a phenomena just for platinum steps. Any surface that binds both species strongly will show this exchange. And on those surfaces, we then also see pH effects, cation effects. They're roughly similar to what we see with platinum, but we're working to see if it's really the same or what.
Great, thanks a lot.
Yeah.
Yeah, I think with that we'll finish the session, and then thank all of you for joining, and yeah, see you in a couple of weeks from now.
Yeah, thank you, Ian.
Yeah, and thanks a lot, Ian, for
That was really thought-provoking. So